Okay, so in the second part of this video, I want to use the polar form that we just used about, that we just learned about in the previous video to understand complex multiplication maybe in a new way. Um, yeah. So let's say that we have two complex numbers now. Let's call them z and w. Oops. Z is going to be r times e to the I theta. All right. And w will be again a complex number, and we're going to again write it in polar form. Let's write it as s times e to the I psi. So I already used the letters r and theta, so I'm just using different letters, but this is still the polar form of w. That's how we should understand it. In particular, s is the modulus of w, r is the modulus of z, and theta and psi are the associated arguments in our exponential terms, right? Or the angular terms. If I'm drawing a picture here, and maybe I should do that, it'll look something like this. Just draw a big picture here. Always good to do. And let's say that maybe z is this number here in the plane. That's going to be the length of that dashed red line there is going to be the modulus of z. That's going to be r, in other words. And this is our theta, the angle with respect to the positive x-axis. And then maybe w is some other complex number like there. And again, we have this sort of thing happening, right? That the length of that green dotted line is the modulus of w, namely s, and this angle here, that's going to be psi, okay? The green angle. All right. Now, can we contemplate for a moment, what is z times w going to be? Well, we learned very early on how to do complex arithmetic. And if we had these in rectangular form, we would do the usual thing. Easy. But here we're going to work with multiplication in the where z and w are in their polar forms. So z is going to be rewritten as r times e to the I theta, while w is written as s times e to the I psi. All right. Now these are four complex numbers here, namely 1, 2, 3, 4, four different complex numbers. We know how to multiply complex numbers, and in particular, we know that complex multiplication is commutative. So it doesn't matter what order I multiply these things in. This is the same thing, in other words, as rs, you agree, times e to the I theta. And what I'm going to do is, let me just take it slow, times e to the I psi. So all I've done is reordered the multiplication of those four numbers. And then e to the I theta times e to the I psi. Again, the exponential function obeys the usual rules around exponents. So we can write this as r times s, and I'm going to put it in parentheses, times e to the I theta plus I psi, but that's just e to the I theta plus psi. All right? So now think about what we're saying here. First of all, we get immediately as a consequence that the modulus of z times, let me back up one step. This, I hope you'll agree, is the polar form of the product z times w. So in particular, this number right here, r times s, is the modulus of z times w. And the angle, and by the way, we're going to come to learn the angle we have a name for that. We call it the argument of the complex number, but we haven't defined that yet. The angle that this complex number makes with respect to the positive x-axis, or the positive real axis, is now the sum of the angles, theta and psi. So the angles add together and the moduli multiply together. So z times w is going to be some new point. Let me color it purple. But in particular, we know a couple things about it. We know that, for example, Um, here's maybe z times w, you can imagine. The new angle, well, the new modulus, let's start with that. The modulus, the length of that purple line is going to be the product of r, the product of the modulus of z with the modulus of w. And the new angle that this complex number makes, this new angle is going to be theta plus psi. And again, you can see that from this polar form for the product of z and w. So it's like complex multiplication. Again, it multiplies the moduli, but adds the angles together. We call some some authors have dubbed this kind of operation an Amplitwist. This is a made-up word. I remember the first time I read it was in the Tristan Needham book, Visual Complex Analysis, which I recommended to you all. And this sort of gives the feeling that what happens with complex multiplication is that we're rotating the plane while at the same time amplifying, by at the same time multiplying or scaling the complex plane. Right? So if you imagine a fixed complex number, maybe a fixed complex number w, and you imagine the impact of multiplying a complex number z by the complex number w, then what you end up seeing is a rotation in the angle of z by the angle associated with w, and then a multiplication or amplification in the modulus of z by the modulus of w. This is the idea. Okay. So that's an Amplitwist. All right. Let's just do some calculations, okay, to make ourselves feel better about all of this. Let's take, for example, z, and I'm going to write it in rectangular form. So let's take z to be 2 plus 2i. All right. And let's take w to be the complex number. How about square root of 3 minus I? All right, you can imagine such a thing. Let's compute the polar forms of each. So first, find polar forms for each. So maybe what we should do first is find the moduli. So the moduli of z, modulus of z, is equal to the square root of the real part squared, which is 4, plus the imaginary part squared, which is also 4. So this is the square root of 8. I don't know why I wrote it like this. Which is square root of 8. And of course, we can write the square root of 8 as 2 times the square root of 2. Now, to find the angular bit, the e to the I theta bit, what we can do is first normalize this complex number z by taking it and dividing it by its modulus. Let's look at z divided by the modulus of z, which we know is going to be a point on the unit circle. Well, in other words, we're going to divide this z here by 2 times the square root of 2. So 2 plus 2i divided by 2 times the square root of 2. The 2's cancel, and we're left with 1 over the square root of 2 plus 1 over the square root of 2 times I. Okay? Now, this should be, because it lives on the unit circle, this should be cosine of theta plus I sine theta for some choice of theta. There's e to the I theta for some choice of theta. And this is like one of those textbook examples where if you know your sines and cosines, you know that this here is the cosine of pi over 4. And this here is the sine of pi over 4. So that you can also rewrite this using Euler's formula as e to the pi over 4 times I. So that z you can write in polar form as z in polar form is the modulus, which is 2 square root of 2, times the e to the pi over 4I that we've got here. Or I times pi over 4. Either way you want to write it is fine. Okay? So that's nice. That's one of the answers. Now let's find the polar form for W. I think you should try to do this for yourself first. Okay? So pause the video, try to find the polar form for W, see what you come up with. Okay, if you tried, just follow the same scheme. Okay, so the modulus of W is going to be the square root of square root of 3 squared, which is 3, plus negative 1 squared, which is 1. And this is square root of 4, which is, of course, 2. So now we normalize W, so that W is equal to, what? Sorry. We normalize W, so we want to do W over the modulus of W. And this is going to be, what? Square root of 3 over I, or minus I, rather, divided by 2, which we can write as square root of 3 over 2 minus 1/2 I. Okay? And now, again, if you know your sines and cosines well, you probably know that this is the cosine of some angle, and this is the sine of that same angle. What's the angle? Right? This is what's crucial to know. And now, I guess I have to figure it out. I think it's pi over 6 less than pi. So I think that's 5 pi over 6. And this one is sine of 5 pi over 6. No. I'm getting that wrong. I wish I had any shame and I could feel embarrassment. But no, I got it wrong. Cosine is root 3 over 2. Cosine of theta is root 3 over 2. So it's positive. And sine of theta is negative 1/2. So it's so it's going to be negative pi over 6. Okay, so this is the same thing as cosine of negative pi over 6. And this thing here is the same thing as sine of negative pi over 6. So in other words, this number, this unit length, this unit modulus complex number is in fact e to the negative pi over 6I. So that putting these things together, we learn that W is equal to 2 times e to the negative pi over 6I. That's its polar form. Okay? Now, what I want to say about the polar form is that it behaves really well when it comes to operations like multiplication and that sort of thing. Okay? So if we call this kind of like part A of this exercise, then part B is, let's, for example, compute z times W. What is z times W? Well, this is now a pretty easy calculation. We just multiply the polar forms together. Z times W is equal to, maybe I'll do this in red, z times W is equal to 2 square root of 2 e to the pi over 4I times 2 times e to the negative pi over 6 times I. All right. And what this corresponds to is 2 times 2. That's 4 times the square root of 2. 4 square root of 2. And then when we multiply the these exponentials together, we just add the angles together. Oh, and so we have to figure out what pi over 4 minus pi over 6 is. Oh no. What is pi over 4 minus pi over 6? Well, I think they share a common denominator of 12. And that's 3 pi over 12. And it's 2 pi over, I think it's just pi over 12. Positive pi over 12. Times I, of course. Okay? By the way, we can also do things like C. What is z squared? Like, we can square numbers. right? And this is easy. If we square these numbers together, we get, let's see, z squared is equal to 2 square root of 2 times e to the pi over 4I squared, which is, so 2 square root of 2 squared is 4 times 2, which is 8, times e to the, now pi over 4I, you square that, that's the same thing as multiplying pi over 4I by 2, so that's pi over 2 times I. Now, in this case, e to the pi over 2 times I, well, what is e to the pi over 2 times I? Pi over, so think geometrically. It's the point on the unit circle in the complex plane, which makes an angle of pi over 2 with respect to the positive x-axis, yes? I don't know if you can hear the birds outside, but they're screaming the answer. The answer is I, right? This, in other words, is 8I. Now, we can try to verify this, can't we? Like, what if we were to take 2 plus 2I, the rectangular form, and square it? So let's just do a little aside calculation. So let's say that we were to take 2 plus z squared is also equal to 2 plus 2I squared. What does this end up being? This is 2 plus 2I times 2 plus 2I. And then we expand this. So we get 4. Hello? Sorry. We get 4 plus 4I plus 4I. Oh, and then 2I times 2I. And what's that? That's 4I squared. Oh, but don't forget I squared is negative 1, so this is minus 4. And then, of course, the 4 and the negative 4 destroy one another. The 4I and the 4I. Even though they're identical twins, they get married, and they become an 8I. It's 2026, people. Relax. Okay, so there's, it's 8I. There we go. You get the same answer, in other words, right? So this just justifies or gives you a little bit more comfort that these moves that we're making using polar multiplication really do work out, even if you use the rectangular representation. Okay, that's enough for this one. See you in the next one.